Hello friends, welcome to my YouTube channel RF Design Basics. So today we are going to study about the applications of the Laplace's equation for capacitance calculation. For this, first of all, we have to write the Laplace equation which we have derived in our last class, and it is given by del square V equal to 0, where del square is Laplacian, and using this equation, by applying the boundary condition, we will find out the potential. So the first step will be to calculate V, that is potential. Then by knowing V, we can calculate electric field by using the gradient of V. And by knowing this and the material properties used for the capacitor, we can calculate the electric flux density D, which is epsilon E. Epsilon is permittivity of the dielectric material used for capacitor. Then in fourth step, we can find the normal component of D. By calculating D here, we can find the normal component of D, which is equal to rho s from the boundary condition. So by knowing the boundary of the capacitor, we can find the normal component of electric flux density, and from the boundary condition it will be equal to the charge density. Once we calculate the charge density, we can calculate the total charge, which is equal to surface integration of the charge density. So let us start with the simple capacitor in rectangular coordinate system, that is known as the parallel plate capacitor. So for parallel plate capacitor, write the del 2V equal to 0, and we will try to solve this. So if we expand in rectangular coordinate system, this will become del 2V by del x square. Then we have del 2V by del y square plus del 2V by del z square equal to 0. Let the potential varies only in one direction. So let's say that potential vary in x direction, for example. In y and z direction it is constant. So we can write del 2V by del x square equal to 0, because potential is constant with respect to y and z. This can be written in terms of full differentiation as del 2V by dx square equal to 0. Now let us solve this and find out the potential. If we solve it, in first step it will be dV by dx, which equal to A, and then we can write V equal to AX plus B. So this is our solution of potential. Let us write this here, V equal to AX plus B. Now we have to apply the boundary condition so that we can find the constant term A and B. So for the parallel plate capacitor, if we have two plates and the field is varying in, let's say, x direction, assume that this is x direction, then at x equal to 0 we can say V equal to 0. So this line is x equal to 0. Similarly, at x equal to D, we can say V equal to V naught. So the boundary condition is in terms of x for the potential. So if x is 0, V is 0. If x is D, V will be equal to V naught. By applying this boundary condition, let us try to solve for the potential. So here if I put x equal to 0, this will become A dot 0 and V is 0. So this says that B equal to 0. Then the second boundary condition is at x equal to d, V equal to V0. Apply x equal to d, so this will become AD plus B is 0, which is equal to V0. This gives A equal to V0 by d. So we can write potential as Ax plus B. So A is V0 by d, x plus B is 0. So this is our potential equation. So we have completed our step 1, which was to calculate the potential. So next we will take gradient of V and we will find electric field E. So from here we can calculate E as minus del V. So this is equal to minus gradient of del by del x of V plus del V by del y plus del V by del z for Ax, Ay and Az direction. This is the gradient formula. If I apply here, since the potential function is only function of x, so this del V by del y and del V by del z will become 0. So we have only differentiation with respect to x. So this we can write as minus d by dx V Ax. So electric field is, if I take differentiation, we will get minus V0 by d Ax. So this is our electric field. And the next step is to calculate D, that is electric flux density. So electric flux density D is equal to epsilon E, which is minus epsilon V0 by d Ax. And now we have to find out which component is the normal component to the plates. So you can see here, these are two plates which is in YZ plane and the normal component is in x direction to the plane. So the normal component will be in the Ax direction. And we have only one component, so that means the normal component is this component only. So we can write dN equal to minus epsilon V0 by d Ax, which is also equal to the surface charge density, rho s Ax. Now next step is to find out the charge, total charge, which is equal to surface charge integration of rho s ds. This says that rho s ds means dot product in the normal direction, so dot product will be 1. So you can directly write this if we represent rho s without this direction. So into rho s, so rho s ds is the surface integration of rho s is minus epsilon V0 by d and then ds. So the total charge will be equal to minus epsilon V0 by d. This is constant, so we can take it out and the integration of surface will be s. The capacitance formula we know, that is the magnitude of charge divided by potential. So here magnitude of charge will become epsilon V0 by d s, epsilon V0 by d s divided by V0. So by cancelling V0, we can calculate capacitance as epsilon s by d, which we have already calculated using different method, and we have got the capacitance value as this.